Hi, in this video we will be talking about vector valued functions and curves. For a flight path of an airplane, as can be seen in the figure below, it is convenient to describe the airplane's location at any given time by the endpoint of a vector whose initial point is located at the origin. To do this, we need a vector valued function that will give us a vector in v sub 3 for each time t. This is the concept of a vector valued function, which is the subject of this chapter and will be defined more precisely later. Curves in the plane and in space using vector valued functions. Lines in R-cube are particular examples of curves in R-cube. In this section, we discuss a more general form of a curve in R-cube. So let f, g, and h be three real valued functions of a real variable t in the domain, which is a subset of the set of real numbers. Then for every number t in the domain, there is a vector r defined by r of t equal to f of t I hat plus g of t j hat plus h of t k hat, and r is called a vector valued function. If r of t is equal to f of t I hat plus g of t j hat plus h of t k hat is a vector valued equation, we write x equals f of t, y equals g of t, z equals h of t. So these are the parametric equations. We can likewise define a vector valued function r in v sub 2 by f of t I hat plus g of t j hat. So this is in the r squared for some scalar functions f and g. Although any variable would do, we routinely use t to represent the independent variable for vector valued functions, since in many applications t represents time. So for example, in r squared, the graph of the curve y equals x squared, or the parabola where x is in the interval -1 to 1, is a parabola as shown in the figure. We may represent the graph above by the vector valued function r of t equal to t I hat plus t squared j hat. So we have x I hat plus f of x j hat. So in this case, our x is t and our y is t squared, where t is in the interval -1 to 1. Hence, if y is equal to f of x, okay, so this is what I've said a while ago, then we may represent the graph by r of t equal to t I hat plus f of t j hat. So again, we let x be equal to t. So for example, represent the following equations in r squared by a vector valued function. So the first one is an equation of a circle of radius r, and it has a center at hk. So take note that cosine squared t plus sine squared t is equal to 1. So we may represent it as notice that we have an r squared on the right side, so we have, or we can use this equation equal to 1 as x minus h over r equal to cosine t, or that x minus h can be written as r cosine t. So if we'll have this, then we'll have x minus h squared, or r squared cosine squared t, plus y minus k over r will also be our sine t. So we'll have y minus k is equal to r sine t. So that we'll have r squared sine squared t equal to r squared. And of course, the left hand side is just r squared times cosine squared t plus sine squared t, which is equivalent to r squared times 1. So we have the correct representation. Again, we will go back to how we represent x as a function of t. So solving for x, we get x equals r cosine t plus h, and y is equal to r sine t plus k. So these are actually the parametric equations, so that our vector r of t will be written as x of t I hat plus y of t j hat. So of course our function, or x is a function of t using this equation, so we'll write r cosine t plus h I hat plus r sine t plus k j hat. So this is our vector valued function given the rectangular equation x minus h squared plus y minus k squared equals r squared. For letter B, we have x minus h squared over a squared plus y minus k squared over b squared equal to 1. And the graph of this is an ellipse if a and b are not equal, or that either a is greater than b or b is greater than a, so we'll have an ellipse. So take note again that cosine squared plus sine squared is equal to 1, or sine squared plus cosine squared is equal to 1. So we will still use the same identity. And of course, we can use x minus h over a equal to sine t, or we can represent, we'll just write it directly. You can actually write x minus h as a sine t and y minus k equal to b cosine t. So that if you substitute this one in the given equation, we will have a sine t quantity squared over a squared plus b cosine t quantity squared over b squared equals 1, which will give us, of course, a squared sine squared t over a squared plus b squared cosine squared t over b squared equal to 1. And of course, we will get sine squared t plus cosine squared t equal to 1, which is a true, or which is a fact. Okay, so going back to our parametric equations, we can rewrite this as x equals a sine t plus h and y equals b cosine t plus k. You can actually apply this for specific values of a and b. Again, we write our vector valued function r in terms of x and y. So we have here a sine t plus h I hat plus b cosine t plus k j hat. Or you may also write this in this manner using components. So a sine t plus h, comma, b cosine t plus k. So either of these two. So for letter C, we have here x minus h squared over a squared minus y minus k squared over b squared equal to 1. So since we have here a difference of square, this looks similar to p, but we have a minus, so we will use a different identity. So we have cosine, or the hyperbolic cosine squared of t minus the hyperbolic sine of t is equal to 1. So we can actually use x minus h over a as cosine h, or cos t, and then y minus k over b as our sine hyperbolic sine t, so that our x minus h will be a cos t, and you can check for yourself if the resulting equation will be true, or this representation will make our equation true. Okay, so again, solving for x, we have a cos t plus h, y equals b hyperbolic sine t plus k, and then we are now ready to write our r, which is equal to x of t I hat plus y of t j hat. So again, this is our parametric equation, or we have written x as a function of t and y as a function of t, so that we'll have a cos t plus h I hat plus b sine or hyperbolic sine t plus k j hat. So this is our real valued function of the given rectangular equation. Example 2.5, a line L in R cube having parametric equations x equals x sub 0 plus ta, y equals y sub 0 plus tb, z equals z sub 0 plus tc can be represented by the vector valued function L of t equal to x sub 0 plus t of a I hat. Again, we are using here the parametric equations, plus y sub 0 plus t of plus tb j hat plus z sub 0 plus tc k hat. So the components here are corresponding to the x, y, z above. Example 2.6, consider r of t equal to a cosine t I hat plus b sine t j hat plus t k hat. The parametric equations of the given curve are x equals a cosine t, y equals b sine t, and z equals t. So eliminating t, we have x squared over a squared is equal to cosine squared t, and y squared over b squared is equal to sine squared t, and these two equations are from the first two equations also above. And then we have x squared over a squared plus y squared over b squared equals 1, and the graph of this is a curve which lies entirely on the elliptical cylinder whose directrix is an ellipse in the xy plane and whose rulings are parallel to the z axis. So this is the graph of r of t. Theorem 2.7, if r is the vector valued function defined by r of t equal to f of t I hat plus g of t j hat plus h of t k hat, and the derivative of r exists, then derivative of r of t is equal to f prime of t I hat plus g prime of t j hat plus h prime of t k hat. So in other words, we just have to take the derivative of each component functions. Example 2.8, let r of t be equal to a cosine t I hat plus b sine t j hat plus t k hat. Find r prime of t, or the derivative of r with respect to t. So according to the theorem, r prime of t is just equal to the derivative of each component. So we'll have, or the sum of the derivative of each component. So we have here derivative of a cosine t with respect to t is negative a sine t I hat. Derivative of b sine t, we just take out the b, and then derivative of sine is cosine. So we have b cosine t j hat plus derivative of t with respect to t is just 1. So we are left with k hat. So this is our r prime of t. Theorem 2.9, if r of t and q of t are vector valued functions, then the derivative of the cross product of r and q is equal to r of t cross q prime of t plus r prime of t cross q of t for all t for which r prime of t and q prime of t exists. So let us now proceed to limits and continuity of vector valued functions. So for a vector valued function r of t equal to f of t I hat plus g of t j hat plus h of t k hat, the limit of r of t as t approaches a is given by the limit of f of t I hat plus the limit of g of t j hat plus limit of h of t k hat, provided all of the indicated limits exist. If any of the limits indicated on the right hand side fail to exist, then the limit of r of t does not exist. So if you notice, the limit of r of t is equal to, or can be derived by finding the limit of each component functions. So therefore, for example 2.11, the limit of r of t in this case would be limit of t squared plus 1 as t approaches 0, limit of 5 cosine t as t approaches 0, and limit of sine t as t approaches 0, using this notation. And it's equal to we just substitute. The first one is limit of t squared plus 1 as t approaches 0. Substituting 0 to t, you will get 0 squared plus 1, so we'll get 1. And then limit of 5 cosine t as t approaches 0 will be 5 cosine 0. And of course, limit of sine t is just, as t approaches 0, is just sine 0. And this is equal to 1. Cosine of 0 is 1, so we get 5. And then sine of 0 is 0. And this is equal to I hat plus 5 j hat. Definition 2.12, a vector valued function r of t equals f of t I hat plus g of t j hat plus h of t k hat is continuous at t equals a whenever the limit of r of t as t approaches a is equal to r of a. So a vector valued function r of t is equal to f of t I hat plus g of t j hat plus h of t k hat is continuous at t equals a if and only if all of the functions f, g, and h are continuous at t equals a, or continuous at a point a, or at a value a. So let us now proceed to derivatives of vector valued functions. The derivative r prime of t of a vector valued function r of t is defined by the limit of r of t plus h minus r of t over h as h approaches 0 for any values of t for which the limit exists. When the limit exists for t equals a, we say that r is differentiable at t equals a. So let r of t be equal to f of t I hat plus g of t j hat plus h of t k hat be a vector valued function. Suppose that f, g, and h are differentiable for some value of t, then the vector r is also differentiable at that value of t, and its derivative is given by f prime of t I hat plus g prime of t j hat plus h prime of t k hat. So notice that what we do here is we take the derivative of each component function. So for example, find r prime of 0 where r of t is equal to t squared plus 1 I hat plus 5 cosine t j hat plus sine t k hat. So I will just use this notation for r of t. So we'll use the components at t squared plus 1, 5 cosine t, and then sine t. And then the r prime of t will be the derivative of each of these components, and derivative of t squared plus 1 with respect to t is just 2t. 5 cosine t, the derivative of that is negative 5 sine t, and derivative of sine is cosine, or cosine t. And then our r prime of 0 is just equal to 0. Sine of 0 is 0 times negative 5, that's 0. And then cosine of 0 is 1, so we have here 1. So therefore, r prime of 0 is just k hat. Theorem 2.17, let R and Q be differentiable vector valued functions. If K of t is differentiable real valued function and C is a real number, then the derivative of the sum of these real valued or vector valued functions is equal to the sum of their derivatives, and derivative of a constant times the vector valued function is equal to the constant times the derivative of the vector valued function R, and derivative of the product f of t times the vector r of t is equal to f prime of t r of t plus f of t r prime of t. So it looks like the product rule that we have for derivatives. Letter D, that's the derivative of the dot product of two vector valued functions. So we have r prime of t dot q of t plus r of t dot q prime of t. And then the derivative of the cross product of r of t and q of t is equal to r prime of t cross q of t plus r of t cross q prime of t. So let us now proceed to integrals of vector valued functions. A vector valued function r of t is an antiderivative of the vector valued function r whenever r prime of t is equal to the lowercase r of t. So note that if r of t is equal to f of t I hat plus g of t j hat plus h of t k hat, and f, g, and h have an antiderivatives f, g, and h respectively, then the derivative of the vector valued function capital R is equal to f prime of t I hat plus g prime of t j hat plus h prime of t k hat, or equal to lowercase f of t I hat plus g of t j hat plus h of t k hat, which is equal to the vector valued function lowercase r. That is the vector valued function capital R is an antiderivative of the lowercase r. So more generally, f of t plus c sub 1 I hat plus g of t plus c sub 2 j hat plus h of t plus c sub 3 k hat is also an antiderivative of r of t for any constants c1, c2, and c3. Let r of t be an antiderivative of r of t. We define the indefinite integral of the lowercase r of t by integral of r of t dt equal to uppercase r of t plus c, where c is an arbitrary constant vector. Hence, we integrate a vector valued function by integrating component wise. So we integrate each of the components. So for example, evaluate t squared plus 1 I hat plus sine 2t j hat plus 4t e to the t squared k hat. By the way, this should have a dt at the end, and this is equal to the integral of t squared plus 1 dt I hat plus integral of sine 2t dt j hat plus integral of 4t e to the t squared dt k hat. And of course, we apply what we learned from finding the integrals, and this is just t cubed over 3 plus t I hat plus we let u be equal to 2t, and so we'll have 1/2. 1/2 du will be equal to dt, so we'll have 1/2. Integral of sine u is negative cosine u, so therefore I should write here negative. This is negative cosine 2t j hat plus, okay, so in this case, if we let u be equal to t squared, then our du is equal to 2t dt. So therefore 2 du is equal to 4t dt. So that this integral here will become integral of 2 du e to the t squared is e to the u, and this will give us 2 e to the u. So therefore we'll have here 2 e to the t squared, 2 e to the t squared, because our u is t squared, k hat. Or this can be written as t cubed plus 3t over 3 I hat minus 1/2 cosine 2t j hat plus 2 e to the t squared k hat. Definition 2.21, let r of t be a vector valued function. So we define the definite integral of r of t on AB as follows. So integral of r of t is equal to the integral of f of t dt I hat plus integral of g of t dt j hat plus integral of h of t dt k hat. Each of the integrals are evaluated from a to b. So for example, 2.22, what we do here is we integrate each or component wise. So we'll have, so this is equal to t cubed over 3 plus, and so we'll have, so this is evaluated from 0 to 1, and then integral of sine 2t is negative 1/2 cosine 2t from 0 to 1, and then integral of 4t e to the t squared is 2 e to the t squared. This is again evaluated from 0 to 1, which will give us 1/3 plus 1, and then negative 1/2 cosine of 2 minus 1/2, sorry, minus negative 1/2, or that would be plus 1/2 cosine of 0, and then 2e to the 1 minus 2e to the 0, which is equal to 4 over 3 negative 1/2 cosine of 2 plus 1/2 cosine of 0 is 1, so that will be 1/2 times 1, or 1/2, 2e minus 2 times e to the 0, which is 1, so 2 times 1, that will be 2. So you can solve for the specific values of this. The second component will be approximately 0.0003, and then this one you can write it as 2e minus 2, or you can solve it. So that is the definite integral of the given vector valued function. Theorem 2.23, the fundamental theorem of calculus. If r of t is an antiderivative of the lowercase r of t on AB, then the definite integral of lowercase r of t dt from a to b is equal to the antiderivative value at b minus the antiderivative value at a. So therefore, we can actually solve for the antiderivative first and then substitute the upper and lower limits. So for example, 2.24, we have integral from 0 to 1 of sine of pi t I hat plus 6t squared plus 4t j hat dt. This is just equal to, so we will first look at the antiderivative of this, or the integral of this component wise, and the integral of this is negative 1 over pi cosine pi t I hat plus 6t cubed over 3 plus 4t squared over 2 j hat, and this is to be evaluated from 0 to 1, which is equivalent to negative 1 over pi cosine of pi times 1 I hat plus, so this is just 2 times 1 cubed plus 2 times 1 squared j hat minus the value when t is 0, negative 1 over pi cosine of pi times 0 I hat plus 2 times 0 cubed plus 2 times 0 squared j hat, which is simply equal to negative cosine pi over pi minus, so we'll just take a look at the terms with the I hat. So we'll have negative 1 over pi cosine pi minus negative 1 over pi cosine 0, or plus cosine 0 over pi I hat, quantity I hat, and then we'll have plus 2 plus 2, so that's 4 j hat, and on the second group we have just a 0 j hat, so that will simply be 4 j hat. And of course we can still simplify this one. Cosine of pi is negative 1, and we have a negative here, so negative of negative 1, that will be positive 1, or 1 over pi, plus cosine of 0 is just 1, so that is just 1 over pi I hat plus 4 j hat, or this is equal to 2 over pi I hat plus 4 j hat. Just write this value, which is of course equal to the given answer here.